Swayam Prabha. Digital India. Educated India.
So, the topic of today's discussion is looking at a Brownian particle in a trap in a harmonic potential. So, since we talked about the dynamics of Brownian particle under free conditions in the absence of any external potential, that basically sets the basis, and from here onwards we can try to apply to more realistic situation as here, that sometimes there is a scenario where a Brownian particle may be confined. It can be spatially confined or it can be confined by a potential. And now the framework that we have, the Langevin equation, can be applied, and then we take into account of the other conditions like applied potential and so on. And from a practical point of view, this is very useful because there is a technique called optical tweezer. Okay. Tweezer, as you know, is a device, a mechanical device that allows you to manipulate objects. You can pick up an object and you can deliver another object in a way that you want to manipulate the placement of the objects. So that's a tweezer that we use in laboratories. Optical tweezer, on the other hand, has a similar kind of a function, but operates with a different kind of mechanics. It uses an optical field or optical force to manipulate a Brownian particle. It can pick up a Brownian particle from one place and then place it in another particle. So that's why it's called optical tweezer. Okay, it is not a mechanical device like a conventional tweezer, but it is an optical technique. Okay, so you can use a laser, create a tweezer-like local force so that the particle can be held, and then you can drag, you can move, you can bring one particle to the other. You can basically make an assemblage of particles. Okay, so this is one of the standard or state-of-the-art technology to manipulate particles. Okay, when I say particle, I am talking about Brownian sized particles. And this has been used quite extensively in soft matter and physics in trying to understand what are the forces acting between a particle on a surface or between two particles, all that. Okay, so gives a very powerful tool. Now, the main working mechanism of this optical tweezer is nothing but a Brownian particle confined to an optical trap or a harmonic potential. So, with that, we would like to now discuss what does the Langevin equation look like for a Brownian particle trapped, and then what we can learn from them and what this optical tweezer instrument actually measures. Okay, so that's what we are going to do today, and you may want to go back and check what we did in terms of dynamic light scattering, which is also an instrument that is devised to measure the particle size based on the Brownian motion of a free Brownian particle by looking at the scattered intensity or the time correlation of the scattered intensity and then manipulating the data. So, this is one level up. Okay, so here we are going to create an optical trap. So, imagine that you have a potential which is harmonic, and this potential is created by a laser beam. Okay, and the particle will be held here. Okay, so now if the particle tries to move up this way or that way, here I am showing in one dimension, then the particle will be experiencing a force that will try to put back into the minimum. So, this particle is undergoing a Brownian motion, okay, and because of this jiggling motion, it will try to go up and down, okay, and then there is the opposite force that tries to push it back. So, this dynamics is something that we can detect by looking at what is the fluctuation in this position, and the fluctuation in position can be used to calculate many of the properties of this particle, including the size of the particle or how stiff this potential is. Okay, so this is one kind of potential. You can also have a potential which is more shallow. Okay, so here we say this is a very shallow potential, this is a steeper potential. Okay, and how you do this? This is something you do by manipulating the laser power and the properties of the laser that you use in confining this. Okay, so that is the context that we want to discuss today. And also I should tell you that the way that this instrument works, it actually uses a time series of data, okay, position as a function of time, which will look like a irregular signal. And as you know, for any signal we use Fourier transform to get the important insight about the signal property. So what I am going to do, which is different from what we did before, is that we will write the Langevin equation and then we convert that into a Fourier space, and then from there we manipulate. We do that because that the instrument that we use here has a way that you record the Fourier components of the motion. Okay, so that's the one difference you will see when we go ahead. Okay, so our starting point in this case is the Langevin equation. Usually we write this inertial term as m dv by dt, but here we will work with the spatial coordinates. So we are writing this in terms of second derivative of position. So x here is the position of a Brownian particle held in a trap. So this entire experiment will happen in a liquid. Okay, so therefore there is going to be a drag, and instead of v I am writing dx by dt, and this term if you see is a random component, random force, and this is a unit normal random variate with the 0 mean and variance 1, and this is the strength of this interaction, the random force, okay, given by the square root of 2 gamma kbt. Again you can see that this is a one dimensional equation. Now extra thing you will see here is this extra force acting on the particle due to the harmonic potential. So when you take the, this is what I was mentioning in the previous class, that you can add any sort of conservative force acting on the particle depending upon the scenario or situation in which this particle is behaving. So here we have a harmonic potential, so of this sort, a quadratic potential, and the derivative of this will give you a force, and that's what this, okay. So k here is the force constant. So you can see that when k is very high, okay, or when k is low, so you have this kind of a shallow potential. When k is very high, you have more like a stiffer potential. So we say this is a stiffness of the confining potential. Okay, so this relates to the stiffness of the potential. In this case, we will convert this equation by eliminating the inertial term, so that we will work in the overdamped limit. So we say overdamped Langevin equation. So this term vanishes. So we basically bring all this, these two terms this side. And dividing by 2 pi gamma this equation, well, just divide this by gamma, So here we have introduced this term, this combination of kappa by eta. It's going to factor in terms of some parameter, because this tells you how strongly the potential is confining. Gamma is something that tells you how effectively the liquid is damping the motion. Okay, so they can be grouped together and they can be called as some sort of term Fc. Okay, so we are defining Fc is k divided by 2 pi gamma. And please note that so here there is another k here. This is the Boltzmann constant that is different from this k. So finally we get this sort of equation. So what is the nature of this equation? This is an overdamped Langevin equation for a Brownian particle subjected to a harmonic potential. So now we will take this equation and then apply Fourier transform to this, and then from there we will manipulate. So this is a dynamic equation that predicts how x will change as a function of time t. Okay, so if you solve, you will get a signal x as a function of t. That's a time series signal. So now what we want to do is we want to change this time domain to a frequency domain. The way you do that is you take the signal, okay, and then you multiply this factor exponential of I 2 pi ft and then integrate over this time t. So usually it is defined from minus infinity to plus infinity. But here we are going to look at a particular time t, capital T, okay, over which we want to observe the signal. So this integration is from minus t half to plus t half, and we want to operate based on this definition of Fourier transform. We want to apply this. Okay, so therefore, one of the things you will see is that this differential equation will become an algebraic equation when you go to Fourier space. So that basically makes us a little bit easy to analyze this equation. So so when you apply this, I will show the results directly. Something you can check later. So when you take this differential equation and apply this Fourier transform, this differential term will become this minus I 2 pi f x, and this term comes as this. In the last term, this Gaussian random variable has to be now written in terms of in the frequency domain. So here it is in time domain. So you can see that it has become more of an algebraic equation. So from here we can try to solve for x. So from here we define, so this basically is going to tell you how the Brownian particle position is going to be represented in the Fourier space. Now we can define what's called this power density function, power density. actually more specifically spectral power density. P of f So, if you see, this is the spectral power density of this function is defined as the magnitude of the square of the magnitude of the function divided by time period t, okay. And by the way, this is a mean square uh, distance. So, this power spectral density, all this says is, in the real space we talk about mean square displacement, right. So, this power spectral density is basically the same thing, but in a Fourier space. And this is something that we can measure using this instrument that I mentioned about. So, now I know the expression for x of, so all I need to do is I take the square of this magnitude of the mean and then divided by time t. So, that would give me my spectral power density. This is something I can measure experimentally using some sort of an optical instrument and electrical instrument. So, in terms of this instrument, what it does is that it detects, as a particle executes motion in this potential well, it detects some sort of an voltage signal, and that voltage signal is actually converted into a time series analysis, and what we actually measure is this power spectral density, okay. Now, from a theoretical point of view, we are trying to get an expression for the spectral power density. By matching the experimental data with this model, we can extract some quantities, okay, in this case the diffusion coefficient and size and all. How did I get here? If you take the first derivative of the dx by dt term that we have, right, so that would yield, when you take a Fourier transform, it will have a negative sign. So, here I start with this expression for x, and note that this is a complex number here. So, I am taking the conjugate of this and I am multiplying both sides. So, therefore, I can write t square. Yeah. So what I have done here is I have multiplied this by the conjugate, complex conjugate, and then in the denominator you will have xc square plus f square, and so then you take the square of the modulus of this. So you will get when you do that, you will get 2d for this, and this would be the modulus square of the Fourier component of the normal random variate, and the modulus square of this would be fc square plus f square. The denominator you are basically simply squaring. So in this case you see that there is one term here and the square of this term here, so you will have only fc square plus f square here, and then the remaining terms remain as such. And one thing you have to note here is when we apply the Fourier transform for the normal random variate, the mean square of that will become the period time t itself. Okay, so that can be substituted here t, and then our power spectral density is defined as the mean square x by t, and therefore this entire expression basically becomes a very simple form which has this diffusion coefficient there and 2 pi square fc square plus f square. What we are saying is that the power spectral density depends on the frequency f by this function. Okay, do you recognize this functional form? This is in the Laurentian form. Okay, so the Laurentian function has this kind of a formula, and this fc here is a characteristic frequency which is defined based on the spring constant kappa and damping coefficient gamma and so on. Okay, so we can measure in the optical tweezer instrument, we can measure the spectral power density, and that experimental data can be fitted to this Laurentian function. Okay, so that's the key of this particular technique. But before we do that, let us just remind ourselves what we know about let's say the mean square displacement as a function of time that we discussed in the last class in the real space. Okay, so let's take log of this and log of this. What would you expect for a over damped Brownian? What's the slope of this line? It's 1, yes. Okay, so you should see something like, so this is the overdamped Langevin free Brownian particles mean square displacement looks like. Now let us say we do the same thing for a Brownian particle under confinement. What would you expect here? So we are saying that if it is a free Brownian particle, it is continuing to increase the mean square displacement proportional to time t. It's a free particle. In this case, I have put this Brownian particle in an optical trap. So what would you expect the mean square displacement to be in that case? You are confined here. Where are you now? You are sitting right here for the last 40 minutes or so, right? You are confined. You are just sitting here. If you are too free to walk in the street, you will be just wandering about, right? So what would you expect about the mean square displacement of a confined particle then? All right, okay. So what will happen is actually you will see some sort of saturation in the mean square displacement a long time, but in a short time you will see a diffusive behavior similar to this. So in the free particle, this is going to continue to grow for a long time. The longer the time, higher is the mean square displacement. When the particle is confined, locally you will see at a very short time scales you will see Brownian diffusion, but then if you wait long enough, you see this particle as if it's going to be confined. Okay, so the mean square displacement will saturate. Okay, so we say this is confinement and this is diffusion. In other words, a Brownian motion. This is important to understand in a real space, because now what we are going to say is that we are going to flip this into a Fourier space, in frequency space. Okay, and you will see something very similar like what you are seeing here. You will see that if you take the time series data of the Brownian particle confined in a potential, and then if you apply this power spectral density transformation, the experimental data would look something like this. So at low frequency, that's long time, you will see some sort of a confinement effect. Short times, you will see this kind of a decay, and this is characteristic of the diffusion, and this is confinement. So you can see there is some sort of a frequency where this change happens from free diffusion to confinement, and that we call as a corner frequency, and that is actually nothing but Fc over here. Okay, and this corner frequency is dependent on the damping coefficient and the steepness of the potential that we apply. Okay, so now what we do, we experimentally measure the spectral power density and then fit to this equation. The fitting constants are d and Fc. Physically, Fc means the transition from diffusion to confinement. Okay, and what is the definition of Fc? This is gamma by k or k by gamma? K by gamma? K by 2 pi gamma, I think, something like this. Okay, so when you fit this constant, you can actually know what is the stiffness of the potential is, how steep the potential was. Okay, and if you change the optical density of the laser, you might have changed the strength of the potential, thereby the corner frequency probably shift here or here. That's one characteristic. And this saturation value, plateau value, will tell you what is this d is, diffusion coefficient. Okay, and if you know diffusion coefficient d, and you can use Stokes-Einstein equation, that is k by t by gamma, and we can get particle size and all that. Okay, in fact, okay, this is what you will do. You will get the diffusion coefficient from the fit. From there, you will get the drag coefficient. From this drag coefficient, you will get the particle size. Okay, and since gamma is now known, you can also find what is the spring constant kappa, because we know Fc also. Okay, so mainly what we are saying is, from this optical tweezer experiment, we can detect what is the particle size and what is the spring constant that we have applied. Okay, because generally when you apply a optical field, you do not know a priori to what extent this is confining. Okay, so this again have to be done a trial and error method. You will see that if the power is so low, you can't hold the particle. If you apply too much of power, you might just burn the particle. Okay, too much of power is bad. So you have to have some sort of an optimal value. You can qualitatively set the power, but what that power means in terms of spring constant, you will get it from here. Okay, and additionally the particle size. This is just a very, very simple introduction to optical tweezer, but the range of application of optical tweezers is far more than what this is. Okay, there's a whole lot of research happening in optical tweezer based manipulation of particles. Okay, force measurements, self assembly, and so on. So I wanted to do more examples of this Langevin approach, but I think I will upload some reading material for you. This Langevin approach has been used in looking at turbulent flows, because turbulent flow also has some sort of irregular and chaotic behavior, and people have applied Langevin dynamics, Langevin equation for predicting turbulent flow. And in polymer dynamics, this Langevin dynamics is used. One of the characteristic attribute of this methodology is that this is called particle level simulations. We are going to the level of the particle itself, and we are individually looking at how the particles are moving. This is called the particle level simulations. Okay, there are other kind where we treat probabilities rather than the specific particles. So those are the other way of looking at the stochastic problems. Right now, this is the most intuitive stochastic process you can think of, because we are talking about the motion of individual particle, just like how we do Newtonian mechanics. Okay, and if you're really interested, there's a whole lot of books and literature out there for you to read. I'll submit some papers on Moodle for you to read. Turbulence, diffusion, sedimentation, and polymer. I mean, whole lot of polymer dynamics is done through Langevin simulations. Okay, so and then we will probably go to another topic on stochastic process, which again will bring to this Brownian motion and its basic mechanisms. But then the formulation, the mathematical formulation can be quite different from this. Okay, going from a particle level to more like a field level or more like a probability level. Okay, so these are all different approaches by which one can approach stochastic problems. What is the how are you feeling about this course? Is it something that you look for this, or is it something that is different from what you signed up for? I would like to get some feedback. I mean, should we change the rigor of the course, or should we make it simpler? Should we do more application? Is it something that you can comprehend what we are doing here, or is it anyone find it difficult? Is too difficult than what you actually expected? Anyone find that way? Are you happy with the amount of material we provide for the study material? Is that enough to supplement your learning? Okay, and so what's the challenge so far? From your point of view, what was the challenge so far, other than attending 8 o'clock classes? Assignments every week. So I have given assignment based on what we have covered. Since this is the beginning of the course, we'll have more assignments. See, assignment giving is one thing. Assignment I give because in the TCF, mostly people say that assignments were not given. I can give assignment, but you should be honest to work it out and submit. See, I see that I can give as much assignment as I want, but then if students are not taking it seriously, and then it doesn't serve the purpose. But the reading material and references there give a lot of further study materials. Okay, I can do that, and we will do some more assignments as we go along. But like I said, this course is not about telling everything about stochastic process. My thing is only giving you pointers. These are the things one can do, but then it's up to the student to pick it up and then do. Like I said, the project will probably make a lot more sense to you if you actually start working on a project of your interest where you apply the stochastic process. That will be the sweetest learning experience for you. Assignments, exams, grade, that is one, but the true learning experience will happen when you actually do some project on your own. You'll write your own code, you will model the problem by yourselves, you'll take the course material as a starting point, and then you'll build on it, you'll change something, you'll adapt that. I think I have taught this course since 2012, okay, last 12 years, and in all these courses people have done projects, and there is a lot of enjoyment of that. So I also kind of request you to pay attention to the project. Okay, so that's something for you also. I mean, you'll feel very good about it. You took a course, you learn some concepts, and you also apply to some project. You may not have to publish it. You don't have to present it in a conference. It is for your own sort of satisfaction. Okay, and this course will have all the elements that you need to give you that kind of an experience. Okay, so but you have to put some extra time. This can't be like any other theory course. You come, do exams and go, and then you do only the minimal thing. That won't work. If you put some extra time and read some more extra material, definitely it will be a good experience. Okay, so all right, so no need to change anything as we go, except giving some extra assignments. That's the only requirement I see right now. Sriram, fine, yeah. All right, okay, so we'll stop here.